For this half of the talk, what I wanted to do was just give a brief sketch of the method of proof, and I'm not wanting to give all details so much as just hopefully concentrate on a few points which might be useful in other problems. The theorem that I'm trying to prove, let me start with Zograf's version of the theorem, which is just for the Laplacian on functions. And get my constants right. Just for emphasis, let me say this is F1. So here we're on a compact Riemann surface given as a quotient of a Schottky group. So being a Schottky group is essentially equivalent to being free. So I've got a free subgroup of PSL2C. With ordinary set omega. The quotient of the ordinary set by gamma is a Riemann, compact Riemann surface. Genus G. Delta 0 is the hyperbolic metric, the hyperbolic Laplacian. So Laplacian and hyperbolic metric. Tau is the Riemann period matrix. S is this classical Liouville action, which I won't write down the definition, but I'll use properties for it. And Q gamma is the multiplier taking the convention that so each group element is conjugate to just multiplying by some complex number, where the if I take the origin to be the attracting fixed point, the modulus is less than 1. And the square bracket here is primitive conjugacy class. And the basic method here is just to vary both sides over the Teichmuller space. So to take the derivative of both sides of this equation and say that they're the same. So that's the overall setup. So let me mention each of each of the factors. There's 4 factors in the formula, so let me mention each of them in turn. And of course, it makes sense to we want to take the logarithm of both sides of this. So what I'm looking for is derivative with respect to mu of log det 0. So TG is the Teichmuller space, and mu is a tangent vector. Which explicitly is a harmonic -1,1 form on the surface. So doing the variation of determinant of Laplacian, probably everyone has done this at some point or another. The zeta function is trace of this operator, and so it makes sense then to no, that wouldn't make sense. Right. And then one just varies the zeta function, and then analytically continues that. So and then trading operators under the under the trace. Oh, sorry. So, remembering that that's the case, we get sorry, 0. Where the so this is the heat kernel. K1 is the Green's function for d bar. And D1 here is the mass operator that takes n m forms to n plus 1 m forms. So so I guess this part is fairly standard, right? Whenever you're doing an argument with the determinant, if you want to do a variational argument with the determinant, you'd write it as this trace, and then the regularization becomes a heat kernel regularization. Then the and then this means that you can write that variation as an integral of a Green's function over the surface. So the usual way to write this is the way it usually appears. Is in this form where the G is df is a fundamental domain on the Fuchsian uniformization on the upper half plane. G is Green's function, automorphic Green function with respect to the Fuchsian group, or is to say on X, and L is the Green's function for delta 0 on X for So the regularization ends up being taking the Green's function on the automorphic Green's function on the upper half plane and subtracting just the diagonal part, the automorphic the Green's function that's just for the upper half plane. Ah, yes, good. Should have put it somewhere here. The factor for the hyperbolic metric. So e to the phi. It turns out to be more convenient. So this is the form that you see it in places. It turns out to be more convenient in this situation, I think, to instead of using the Green's function for the Laplacian, it works out more nicely, and it becomes essential when you're working on an nth power of the canonical bundle, rather than using the Laplacian for the Green's function for the Laplacian, to use the Green's function for d bar. So here it's really just a question of taste, I guess. But it becomes important later. So oh, and this vertical bar with the triangle is on the diagonal. So this is in two variables, z and z prime. This is derivative with respect to So you have these kernels in two variables. Take the derivative with respect to each, restrict it to the diagonal, and multiply by row inverse. Equivalently, take this kernel where K1 is Green's function for d bar on x lifted to the upper half plane. So the automorphic function, Green's function for d bar, automorphic with respect to the Fuchsian group, uniformizing x. And R1 is the Green's function for d bar on the upper half plane. And I guess the non-standard part of this is where this kernel just by sort of explicit computation, turns out to be the same as this one. So you can drop this automorphic derivative and replace this Green's function for the upper half plane just with the singularity. It's just a direct computation. This becomes more important if you're over the nth power of the canonical bundle. There's sort of a trick there for n greater than 1. Which is maybe worth pointing out because I probably won't get to n greater than 1. For n bigger than 1, the naturally occurring kernel is dn of kn minus rn, where kn and Rn are the Kn is the Green's function for d bar n. In other words, d bar acting on the nth power of the canonical bundle. So that's the thing which you get just by sort of following your nose and finding the variation for the log det Laplacian. The non-obvious thing, which comes from physicists, is that this kernel is the same as this one. And there's sort of a physical heuristic for why that makes sense, which I've never really 100% understood. And I still don't quite know what this means mathematically. But this kernel is very intractable to work with explicitly, and this one actually turns out to work out very nicely. And there's some sort of it's somehow respecting the Poincare ideality between n and 1 minus n, but I don't quite understand why it works. But that part's crucial. And then this kernel is a projective connection. So it's not quite automorphic. Let me give this a name. This is T1 of Z. so the thing that you would expect, so what I'm doing here when I'm saying this derivative is in the direction mu is this integral against mu, what I'm saying is that this integral kernel is a cotangent vector. So this is supposed to be a cotangent vector in the moduli space, which is in other words a quadratic differential. And as long as J is an element of the group, this is correct. But it's not correct in general. It's if you make a more general change of coordinates, this varies by the Schwartzian of that. The Schwartzian derivative of that transformation. So, so this is the point at which we change from the upper half plane, which is sort of the essential natural place to do this, and switch that from the upper half plane to the Schottky group. And you can do this at the price of picking up this Schwartzian derivative. The reason that appears is because of this regularization. So the regularization is not quite, the K1 is automorphic in each variable, but the regularization is not. So what that gets you in the end is that this that the variation of the determinant is written in terms of this, the integral of this kernel over a fundamental domain for the Schottky group, plus the Schwartzian of J, where J is the covering map. So J is mapping the upper half plane to the ordinary set of the Schottky group, so it maps the fundamental domain in the upper half plane to the fundamental domain on the Schottky group. T is this kernel. T1 of Z is the kernel that that appeared back in this formula. Pardon me? Oh, yes. I see what you're saying. Right. Sorry. Yes. Sorry. Thanks.
J is a map from H to omega. So
Right. Right. So I'm being a little sloppy with domains here. So what I mean here is that this is d of k1 minus 1 over pi 1 over z minus z prime mu d2z. Oh, and sorry, I'm missing a 1 over 6 pi. That it's the integral over the Schottky fundamental group, or Schottky fundamental domain of the z here is the local parameter for the Schottky group, and k1 is the Green's function for d bar on the automorphic with respect to the Schottky group, which is the image of the k1 for the upper half plane under J. Does that answer that question? So meaning actually that. So I guess really I should be putting in a J or J inverse somewhere here. Is that so I'm taking the I have this kernel in the upper half plane, and then I'm taking the image of that, or I guess pulling back through J. So the so the overall thing has been to take sort of this standard variation of the log determinant in terms of the Green's function. Make this slight rewriting of the Green's function, which actually turns out to be useful. Transfer the Green's function, or the kernel you get from the Green's function, from the upper half plane to the Schottky domain. The Schwartzian of J here turns out to be the derivative of the log of this term. So the Schwartzian is the derivative of the Liouville functional S. So this is where the Liouville functional comes out. Then the strategy is to write an explicit formula for explicit series for the Green's function, which is relatively standard, and then that explicit series is going to be identified with the variation for F, which comes out as an explicit series because you have this explicit product. So let me just say that briefly. So this series is correct for any group uniformizing X. So you can write this either on the Fuchsian or the Schottky group, but it's on the Schottky group that you can make this identification. This is just taking the singularity for the d bar Green's function is a 1 over z, and then you're just making that automorphic and subtracting the projector onto the kernel. So this is the projector onto the kernel because phi 1 through phi g are basis for holomorphic differentials. The imaginary tau is the inner products, and then I'm using the upper index to write inverse. So this is the inverse transpose times the phi z's, and the fk is the integral but I need a bar. So when you take d prime of this, you get the projector onto the kernel, and here you get the 1 over z squared singularity, which you'd expect from this kernel. So this is a series expansion for the Green's function. So this gives the variation of the log determinant as an explicit series, this first series with respect to the group is going to be what's identified with the variation of this thing, of the function f, and of course the part of the Green's function that is the projector on the kernel is what will be identified with the variation of the matrix of inner products of the basis for the kernel. So the let me just briefly say the kernel part, derivative of log det imaginary tau, is the trace of this matrix let me just write n for the matrix imaginary tau. So this is n inverse d n. So the log det is trace of log, and then you take the variation of the log of the matrix, and and the non-trivial part that I'm using here is that the derivative of njk is Vj times Vw. This is due to Rauk. And so if you take d prime of this and you put it on the diagonal, you get this expression, which is the variation of the log determinant. The exponential minus 1 over 12 pi s where that comes in is that the derivative with respect to s, derivative of s over the Teichmüller space is 2 times the Schwarzian of this map from the Fuchsian cover to the Schottky cover. So this is result of Takhtajan Zograph. And so then the remaining thing is the function f of 1. The log of F1 is sum over gamma, sum over n. You can write the q gamma is modulus less than 1. So you can write this log of 1 minus q gamma as a series itself. So substituting in a Taylor series for log and switching the order of summation, you end up with a minus that. And so the derivative is and then finally, this is where the Teichmüller theory appears. Is the derivative of the log derivative of the multiplier. So q gamma is the multiplier for the group, and the log derivative of that multiplier can be written as an explicit series over the group, and this series is where here the A gamma is the A gamma and B gamma are fixed points of the element gamma, and the sum here is over left cosets of the cyclic group generated by gamma. So that's where you it's in this series that you get the sum over primitive conjugacy classes gets transformed into a sum over the whole group, because you're identifying it with the Green's function, which is a sum over the whole group. Your sum for the variation of log f, the sum over conjugacy classes, then a sum over m, and then this sum gives you a sum within the conjugacy class. So you replace this derivative with this sum, and collapse the sum within each conjugacy class. And when you do that series manipulation, you end up getting exactly this series, the first part of the series for the Green's function. So I don't know if this has been at all helpful. The surprising, or at least the interesting things to me out of, in possibly other contexts, is one is how much easier it is to use this form of the kernel for the variation of the determinant Laplacian, rather than the one that naturally occurs. If you're working with an nth power of the canonical bundle with n differentials, this thing is kind of crucial. The other point is using the freedom of having a projective connection to change from one covering to another. And I guess the other point where the technicolor theory actually comes in, at least in the computation, is the fact that it's generally possible, if you have something that you're trying to vary, like here the multipliers for the group, to write that variation explicitly as a series over the group uniformizing the surface. This comes from the just sort of writing out there's an expression for the variation of a function in terms of integral kernels given in Alfor's book, and that part is maybe not obvious. The things get more involved for n differentials. Although the general steps are the same, the one additional thing which becomes relevant is we're using the fact here that this actually turns out to be a holomorphic quadratic differential with respect to the group, and so it's really representing a cotangent vector. Once you twist with the nth power of the canonical bundle, this is no longer a holomorphic quadratic differential, and so you have to make a holomorphic projection, and that's almost impossible to do explicitly. And the way of avoiding that is by actually trying to compute this integral by the way of contour integrals over the fundamental domain. All right, I apologize if this has been opaque. Thanks.
Thank you very much.
No, the proof that we did for the quasi-Fuchsian case is actually very different. What we did was we used the Docker-Fong formula for Fuchsian groups, and knowing that equality was true for Fuchsian groups, the Fuchsian groups form a totally real subspace of the quasi-Fuchsian space thought of as a complex manifold. And so we basically just wrote down a formula which restricts to the Docker-Fung formula on that real submanifold, and proved that formula we wrote down was symmetric with respect to conjugation with respect to that real submanifold. And using a variant of Schwartz reflection lemma showed that then that extension had to be unique. So we cheated for that one. It's possible in principle, I think, to go through the whole variational method for quasi-Fuchsian. That's how I started doing it, but it's technically a little more awkward. And this was already awkward enough. So yeah, we did use a very different method for quasi-Fuchsian.
How do you prove the relation of two determinants corresponding to the two Riemann surfaces normalized by a quasi-Fuchsian?
Right. That's a cheat in that we make this.
What is essential?
Yeah. What's essential in that is that this. If you restrict this to the on the Fuchsian locus, so for a quasi-Fuchsian group, if the Riemann surface Y is just the complex conjugate of the Riemann surface X, you have a Fuchsian group. This is the Docker-Fung formula. The Fn becomes the Selberg-Zeta function. Determinant of Laplacian on X bar is the same as determinant of Laplacian on X. So it's a square of the Docker-Fung formula. And the S reduces to to a constant on that sublocus. So then this formula is if let me take so this function it's pluriharmonic by the local index formula, and we know that we use unique extension theorems. Oh yes, n sub x is the matrix of inner products for a basis of the kernel of the Laplacian. In this case, for Schottky groups, we had to do an extension of the classical, the usual normalization for the kernel is the usual Riemann normalization, where the integral over the A cycle, integral over AJ of phi k is delta JK. We did an extension of that, which normalized it by Bayer's cohomology. In this case, the choice of the basis is actually irrelevant. We can choose any holomorphically varying basis for delta x. But for delta y, the basis has to be relate it to the basis for delta x by a sort of a Bayes reflection map. So there's the basis for y has to be chosen in a particular way with respect to the basis for x.
You can consider determinant Laplacian acting on some bundle, flat
Mm-hmm.
say bundle. In that
Yeah.
case, you have the same formula.
Yeah. So you can twist with a flat bundle, and this is a computation which I mostly completed, and for reasons unknown, I just never have completed it. You do end up with essentially the same formula, but there's a dependence on the flat line bundle as well. So there's a factor which depends on the character defining the flat line bundle. And I can't reproduce what that is exactly, so I don't want to commit myself.